Okay, thanks everyone for coming to this session today. Today we're very happy to have Alexander Pruss from Baylor University. Alexander is a professor in philosophy, and he has done many fantastic work on probability and also metaphysics and causation. Today he's going to talk about regular, hyperreal, and qualitative probabilities invariant under symmetries. Alexander, the floor is yours.
Okay, thanks. So this is going to be like, a stereotypical interdisciplinary talk, namely not very clever on the math side and not very deep on the philosophy side, but it's what I've got. Okay, so start with a little bit of standard sort of background. So, okay, imagine we've got like this little foam dartboard like I've got in my office, and I shoot blowgun darts at it when I'm bored. And suppose the blowgun darts are like either perfectly thin at the ends or perfectly symmetrical, so they define an exact point, right? And so here's some events that could happen, or perhaps couldn't happen. The dart turns into a square circle, becomes immaterial perhaps, something weird like that. Second option, dart hits the exact center. Hasn't yet happened, but it would be nice if it happened. Dart hits horizontal line through exact center. Dart hits horizontal or vertical line through exact center. Or dart hits a point with coordinates, one of which is rational. Okay, so we've got like a bunch of events here, 5 events, and it seems intuitively right to say that each one is more likely than the ones that came before, right? So there's no chance of it turning into a square circle, but there's some chance of it's hitting the exact center, and intuitively, infinitely more chance of it hitting somewhere on the horizontal line through the exact center. There being infinitely many points on the horizontal line, and only one of them is the exact center, and they all seem to be equally likely, right? And it seems like hitting the horizontal or vertical line through the exact center is about twice as likely as just hitting the horizontal line. And then the last option seems to be way more likely. In classical probability theory, all of these are equally likely because they all have probability 0. So classical probability, right, in these kinds of cases, continuous processes famously violate this Bayesian principle of regularity, that a possible result is more likely than a contradiction. So the first result in my 5 examples was a contradiction. The next ones on classical probability were no more likely than it. They were all 0 probability. So it would be nice to have regularity, but we're not going to in classical probability. Here's a variant statement of regularity that I will at times use. If A entails B, but B doesn't entail A, then B is strictly more likely than A. So we want a probability theory that allows comparisons of classically null probability outcomes. And people have come up with a number of options, and I'm going to talk about 3 briefly, and then discuss a problem that people have raised for these, and then discuss some math that's at least interesting to me that characterizes exactly when the problem comes up, and I'll end with a little bit of philosophy where I'm not very sure of the philosophy. So the first option is full conditional probabilities, or Popper functions. So the idea here is, instead of assigning probabilities to individual outcomes, what we do is we do conditional probabilities as a fundamental thing. So we assign a conditional probability to one thing given another thing. And we have some standard axioms. If you hold fixed the thing you're conditioning on, then you got a probability function that's finitely additive. You've got some little compatibility conditions, C2 and C3. By the way, do people see my cursor when I'm moving it around or not, if I'm pointing with it?
Yes.
Okay.
Yes.
Oh, good. Once we have this, we can then do some comparisons. So we could say that some event B is at least as likely as A, if and only if when we conditionalize on the disjunction of the two events, B comes out at least as likely as A. And we can say B is more likely than A if we've got a strict inequality. A nice thing is that regularity in at least the sense of every event being more likely than the empty event, or every non-empty event being more likely than the empty event, is automatically guaranteed once you have this, as long as you've got this defined for every pair of sets A and B would be non-empty. So, and we can, if we want, come up with a full conditional probability like this that verifies the 5 null event rankings in the Dart case. So far it sounds good, but there's going to be disappointment ahead, as a number of you probably know. Another option, we bring in infinitesimal probabilities. So we want to say, okay, we've got like these 5 events, and the first one just has probability 0, and the other 4 have infinitesimal probabilities. So their probabilities are bigger than 0 and smaller than every positive real number. So they're infinitesimal. As Bishop Berkeley put it, they are ghosts of departed quantities. And we can, of course, formalize this. We can have a hyperreal field which behaves with regard to first order properties just like the reals, and it includes infinitesimals and infinite numbers. And then we just throw in our standard axioms of finitely additive probability. We can't have countable additivity because it just doesn't make sense to do countable addition in the hyperreal field. We can add an axiom of regularity, which just says that events that aren't empty have non-zero probability, and that's equivalent to saying that if A is a subset of B, a strict subset of B, then the probability of A is less than the probability of B. And again, we can construct a regular hyperreal probability that verifies the intuitive things I said about the Dart throw events, at least these ones. And once we have regular hyperreal probabilities, we can define full conditional probabilities using the standard classical ratio formula, because we need regularity because that ensures that the denominator, the probability of B, is always non-zero. And there's a nice little result from 1968 by Krauss that every conditional probability can be defined in terms of some hyperreal probability. So given a hyperreal probability, you can get a conditional probability. Every conditional probability comes from a hyperreal probability in this way. Oh, I guess I should have said, that's a little mistake. It's this ratio, but we actually want to take the standard part of it. We drop any infinitesimal parts on that. Okay, so that's the second way to go. Here's a third way, qualitative probabilities. So qualitative probabilities are, here we dispense with numbers or even hyperreal numbers. We just compare things directly. And so we have some relation approximately less than or equal, which is a relation on the set of all events. And I'm going to, throughout, just take the set of all events to be the set of all subsets of our space omega that we're working on. And we're going to have 3 axioms. One is that it's a preorder, which means it's reflexive and transitive. So everything is less than or equal to itself. And if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. We've got non-negativity. The empty set is the least likely, or is a least likely event. And we've got finite additivity, which means that A is less than or equal to B. I'll just say less than or equal. It's easier than approximately. If and only if you add some disjoint thing to A and to B, and you still have this exactly the same relationship. And then we've got like sort of a bit of notation. So we say A is strictly less than B if and only if A is less than or equal to B, but B isn't less than or equal to A. And A and B are approximately equal, which I'm going to read as have the same probability or equiprobable, provided that A is less than or equal to B and B is less than or equal to A nice condition to have, though we won't always need it, is totality, which says that any two events can be compared. Either one is more likely, either one is at least as likely as the other is at least as likely as it. We can do a fair amount actually without totality, but we're going to assume it at times. And regularity now is a statement that says that every non-empty event is more likely than the empty event. And that's equivalent, given the other axioms, to just saying that if A is a proper subset of B, then A is less than B. And once again, we can, if all we want is to have these 5 events in our Dart case and rank them in a strict way, we can do that. Any hyperreal probability defines a total qualitative probability just by saying that B is at least as likely as A, provided the probability of A is less than or equal to the probability of B in a pretty obvious way. In fact, any classical probability defines a total qualitative probability. Though if the hyperreal probability is regular, then the qualitative one is regular, which is kind of nice. Another more than half-century old theorem by Sidemer, Kraft, and Pratt, though, notes that, interestingly enough, you cannot always define a qualitative probability using hyperreal. So we have this nice fact that every conditional probability could be defined using hyperreal. It's not the case that every qualitative one can be defined using hyperreal. In fact, even if the space we're working with is finite, which is a cute little result. So it's, in some sense, this is more general than the hyperreal probabilities. Okay, now, but so I said you can use these to rank the events, but there is a problem that comes up, which is that we usually want to say something more than just, our probabilities rank these 5 events correctly, right? We want to rank other things correctly. We want to say other stuff that makes sense. And one of the things that intuitively we want in a lot of cases is to have certain symmetries. So often we are dealing with, when we're thinking about things, cases which seem to have a symmetry to them. So in the case of a uniform dart throw, you translate a region or you rotate it, and it shouldn't change the probability of hitting that region, assuming you're shooting uniformly. If you have some skill, then it's not uniform because you're more likely to hit closer to the center, hopefully. And there may be some rotational asymmetry in real life because of the physical processes. But if it's truly uniform, intuitively, it should be translation rotation invariant. Or we might have another case we'll talk about is a spinner, where you just spin something until it stops at some number. Intuitively, if it's really truly a fair spinner, it's going to have probabilities that are invariant under rotations about the center. So if we've got like some event that's, we've got the circle and then we've got some event here, well, that event is going to have the same probability as a rotation of it by any angle. Here's another kind of case that's interesting, is all sorts of infinite sequences of independent tosses of a coin. Here, there's sort of 2 kinds of intuitive symmetries. They're kind of different. One kind of symmetry is, you would think it doesn't matter how you relabel the coins. So you've got an infinite number of coins, you toss them. None of the probabilities should change under any relabeling of the coins. So that's a permutation symmetry. You permute the coins and you should have the same probability. So let's say you're wondering, how likely is it that the even numbered coins are all heads? You permute the coins and you relabel the coins in some way. If they're all really independent and all of the coins are the same, really no permutation should change that probability. But a second kind of symmetry that comes up for coins is what I call reversal of a subset. So that's a symmetry where you've got like a whole bunch of coins, maybe they're numbered 1 through 1, 2, 3, and so on. you fix some subset of them, maybe the even numbered ones, and you say, hey, after my experiment of tossing the coins, I'm going to reverse the ones in this subset. So I'm going to like take all the even numbered ones and flip them over again after the experiment. That shouldn't change anything probabilistically. Like, it would be really weird to think, I'm going to play some game with infinitely many coins, and we come up with some agreed pricing as strategy for the game, and you and I have this nice agreement of what the payoffs will be, and then I say, hey, would you let me flip over the even numbered ones at the end an extra time? Please, it's really important to me. Well, the more I insist, the more suspicious you're going to get that the coins aren't fair, that there's something different about the even numbered ones, or that the head, right? And yet, if they're really fair, flipping over a whole bunch of them an extra time shouldn't change any of the probabilities. So that's a second kind of symmetry we want on coin tosses. Another one case, a countably infinite lottery on the integers. So you've got a ticket for every integer. Seems like you shouldn't result, how likely it is that some subset contains the winner shouldn't change if you translate that subset over by some distance, if you flip it over, or even permute it in some other way, again, because it seems like all the tickets are on par, so no relabeling should matter. It's like John Norton talks of lotteries as defined by relabeling, not making a difference, and that seems intuitively right. Okay, so we can make this pretty general. We've got a group of symmetries. That means that we can like, grouped here means we can compose them and reverse them. So rotations, right? You take two rotations, you combine them, you get another rotation. You can reverse a rotation and get back to where you were. And they act on some space. Interestingly, for me at least, some of the cases will be ones where the symmetries act on a larger space than the one that we're interested in. So for example, in the dart throw case, we've got a region, let's call it omega, which is the circle within which I'm throwing the darts. But translations act on a larger space, namely all of the two-dimensional plane. You can translate some little region of the circle and might translate out of the circle. So the group of translations is going to be able to move things in and out of that space. But we want to have some kind of intuitive idea that if you take some subset of, if we've got our group of symmetries and you have some subset of our space omega that we're going to define a probability for, and then we shift it over by some member of the symmetry group, and the shifted version is still in our space omega, so then they're equally likely. That's what the concept we're trying to capture here. So in the dart case, our bigger space is all of the plane, and our probabilities are on the set of things of distance ones, say from the origin. In all the other cases I'm talking about here, the space I'm working with just is omega, and all the rotations don't get you out of the spinner, permutations and reversals don't get you out of the coin tosses, and the lottery isn't, you don't leave it by translations, reflections out of the permutations. So there, it's the sort of simpler case where all the both spaces are the same. Okay, so we've got some kind of intuitions about symmetries. And we can now define what it means to say that our non-classical probabilities satisfy these. So we can say for conditional probabilities, okay, we want that when we apply a symmetry to some event A, we have the same conditional probability as long as both of the events are inside this thing we're conditioning on. For hyperreal, it's a little simpler. And for qualitative probability, we just say each event is each event is equiprobable with what we get when we apply the symmetry to that event, as long as by applying the symmetry, we don't leave our space omega. And that's going to be a condition we have in all of these cases, that we don't leave our space omega when we apply the symmetry. So the big question I want to ask, the big mathematical question here, which has been partly answered in the literature, but only as partly, is under what exact circumstances do there exist regular non-classical probabilities of these three kinds, conditional, hyperreal, and qualitative, that are invariant under a group of symmetries. We have like one nice little positive result. There's actually a number more, but it's kind of nice to remember. If our group of symmetries is commutative, so it doesn't matter which order you apply them, then you automatically get full conditional probabilities, or you can get full conditional probabilities that are invariant. So the abelian case where it's commutative is going to be kind of nice. So you rotate things on a spinner. You can rotate, it doesn't matter which order you rotate if you do two rotations. On the other hand, if you rotate things in the plane, you can rotate around one thing and then rotate it around a different center. It matters which order you rotate. So it's going to, for some of these things, we're going to have commutativity. For some of them, we're not going to. Okay, so that's the mathematical question I'm going to give a complete answer to. Under what circumstances can we satisfy symmetries? And the answer is going to be not that many. And it's going to be, it's going to differ between the three types of probability. So here's a little warm-up for this, how this stuff works. So imagine we have a fair spinner that selects a random point on a circle. And so we've got this random point. And now we do this. Here's a symmetry, rotation of the selected point by some irrational angle. So that's alpha rotates by an irrational angle. And we have some starting point X selected, and then we form this interesting little set where we take our point X on the periphery of the center of the circle, then we rotate it by alpha, rotate by alpha again, and keep on rotating. Because alpha is irrational, we will never come back to where we started, right? To come back to where we started, we would have to rotate by a multiple of 360. No amount of rotating by an irrational angle is going to give us a multiple of 360. So this is the set of where we have a point and then rotated by alpha is an infinite set. All right, it's an infinite set. What if we take this infinite set, and it's a dense set, like it's got points arbitrarily close together all over the edges of it. It's a countable infinite set. Very nice little set. I think it was discovered, I don't know, maybe by Banach, somebody in around one of those people before they discovered the Banach-Tarski paradox. Actually, this set got discovered. And here's the really cool property of the set. If you take the set and then you rotate the whole set by an extra rotation of alpha, you have the set alpha x, alpha squared x, alpha cubed x, and so on. This set is clearly a subset of this one, of the original one. And it's a proper subset of it because it's missing x in it. So this is like one of those really weird sets where I call it semi-paradoxical, because there are going to be worse ones than that, but it's semi-paradoxical in that there's an angle by which when you rotate it, you get a smaller set. It's very strange. But it immediately means that if you cannot have a regular hyperreal probability on the spinner that's invariant under rotations. Why? Because that hyperreal probability will assign a non-zero value to A. If it's invariant, it'll have to assign exactly the same value to the rotation of A, but the rotation is a proper subset, and that violates regularity. Okay, so we can't have that. So no regular hyperreal probability for subsets of the circle under rotation. Ditto, no regular qualitative probabilities that are invariant because again, we would want alpha A to be less likely than A because it's a proper subset, but that can't be if it's invariant because one is a rotation of the other. Interesting fact though, if you do have a, I said full qualitative, this is meant to be full conditional. There is a full conditional probability because our rotations are commutative. So we can actually get conditional probabilities, but cannot get hyperreal or qualitative ones that are regular. So hey, that's a point. If we want to do a little bit of a shallow philosophy score keeping, that's something in favor of the conditional probabilities, is they don't have trouble with this set, and they don't have trouble with rotation on a spinner. Here's another little thing. This is Williamson's famous paper on infinite sequence of coin tosses. So let's say I've got an infinite sequence of coin tosses numbered with positive integers. Intuitively, my probability should be invariant under shifts or translations. The probability that tosses 2, 3, 4, and so on are all heads should be the same as the probability that tosses 1, 2, 3 are all heads. At least that's an intuition that a lot of you share, though there's a large literature now disputing the intuition. And we should intuitively get invariance under coin reversals. So if you like take some set of results and reverse one of the coins, you should still have the same probability. Well, if you do that, then the probability of having tails followed by only heads is going to be the same as the probability of having heads followed by only heads. And those add up to the probability of having only heads from the second toss on by additivity. So if these two are equal, they must each have a probability, half of this one. So the probability of this is a half of this thing, and the probability of this is a half of the probability of this one. So we get this, but this violates invariance under shifts because H2 is just a shift of H1 as long as these are non-zero. So we learned from this little example that when we have coin tosses, there is no regular hyperreal probability or qualitative probability or even full conditional probability that has invariance under shifts and coin reversals. So that's a negative result. Okay, so those are two little examples. Now let's get to some theorems. We need this complicated concept of equidecomposability, which is somewhat complicated and hard to pronounce for me. So we can say two events are equidecomposable with respect to some symmetries if and only if you can partition these two events into disjoint subsets and then move those disjoint subsets around to get the disjoint subsets of the other one. So the idea is we can cut up A into n pieces and cut up B into n pieces and then move, the pieces of A by the symmetries G to get the pieces of B. Okay, so we like slice it up and move them around by our symmetries. Now, nice thing is that if we've got probabilities that are invariant under the symmetries, they should treat sets that are equidecomposable in the same way. Because A1 will have the same probability as B1, because B1 is just an application of G to A1. B2 will have the same probability as A2, because it's just an application of, I guess this is supposed to say GI, G2 to A2, and so on. So if we've got invariant probabilities, they're going to treat sets that can be equidecomposed under these symmetries in the same way, and so they will assign the same probabilities to them, and we can say that in a fairly precise way here. The concept of equidecomposability comes out of an analysis of the Banach-Tarski paradox. which says that you can take a ball and divide it up into a small number of pieces and make 2 balls out of it. In terms of the equidecomposability, the way the Banach-Tarski paradox goes is you say if you've got a ball C in Euclidean space, then you can partition that ball into 2 subsets A and B such that each of these subsets is equidecomposable with the whole thing under rigid motions, so under rotations and translations. That's really weird, right? I mean, it's like you could, if you imagine the ball made out of gold, it seems like you can cut it up into 2 pieces and make out of each one a new, and each one is equidecomposable with the original. So hey, you could now sell the 2 pieces to different people, and each person can then cut it up and get the original back, and you've doubled the gold. Well, except of course it doesn't work with gold, because gold is made out of atoms, and the atoms are bigger than points, and this requires cutting very finely into points, and so you can't really do it with real atoms. So that makes it a bit less paradoxical. When Richard Feynman was given this paradox, he asked, does it work for an orange? And when he was told it doesn't, he said, oh, not a big deal. We can learn from the Banach-Tarski paradox that there isn't going to be a probability invariant under rigid motions on the ball in Euclidean space that's definable for these partitions A and B. So these are non-measurable sets. Okay, so now some results. So suppose we've got, this first thing is really well known. So we can say that a set is paradoxical, provided that you can divide it up into 2 subsets, and each of those subsets is equidecomposable with the original. So it's like the ball in the Banach-Tarski case. And if we've got a subset that's paradoxical in our space, then we cannot have invariant conditional probabilities and nor invariant hyperreal probabilities that are regular. Just things aren't going to add up, because it's going to have to assign the same probability to E1 as to E, the same probability to E2 as to E. And so it's going to have to assign, wait, now it's looking like by additivity, it'll have to assign twice the probability to E as to E1, but it's the same probability to E1 and E. And if E is non-empty, that probability has to be non-zero by regularity, so that can't be. And you can also check that the same argument works for qualitative probabilities. You just cannot, if they're all equidecomposable, they'll all have the same qualitative probability, but wait, they can't, because this is a proper subset of that. And we can have this concept of semi-paradoxical set, which is a little bit less paradoxical, where it's a set that's equidecomposable with a proper subset. So here, if it's non-empty and paradoxical, it's semi-paradoxical because it's equidecomposable with the proper subset E1. So one example of a semi-paradoxical set is that little subset of the circle, which when you rotate it, becomes a subset of itself. That's equidecomposable with a subset in just one piece. We don't actually need to do any cutting. And we can show that if it's semi-paradoxical, you don't have invariant regular hyperreal probabilities. You don't have invariant regular qualitative probabilities either. Why? Because if it's equidecomposable with a subset, it would have to have the same probability as that subset, but that would violate regularity. And in both cases, the same reasoning. Okay, so we have a necessary condition for there to be invariant full conditional probabilities. There is no non-empty paradoxical subset. And we have a necessary condition for there being invariant regular hyperreal or qualitative probabilities. It has no semi-paradoxical subsets. So here's a fun fact that I've proved recently. These conditions are also sufficient. So the only thing that can go wrong with finding probabilities that are invariant under symmetries is paradoxical or semi-paradoxical subsets. Moreover, here's another little surprising fact. If you've got this problem, that problem always comes up for a countable subset. So it turns out, as long as you can define your invariant conditional probabilities or hyperreal or qualitative ones for all the countable subsets, that's good enough. So that's kind of neat. But it's still going to be hard to do this. I found some surprising things here. I found it surprising that but that one, maybe I shouldn't have, that you always, if you have a counterexample, it's always countable. You can always find a countable one. I found very surprising that the existence conditions for the hyperreal and qualitative cases are the same, given that it's not true that qualitative probabilities always derive from hyperreal ones. It's a fun fact that if our group is abelian, there are no paradoxical subsets other than the empty set. And then there's this little characterization that's sort of based on ideas in a recent piece by Scarparo of what a semi-paradoxical set is like. So remember, the semi-paradoxical sets are the ones that block invariant, regular, hyperreal, or qualitative probabilities. So here's how to what it means to say there is a semi-paradoxical set. It means there is a point in our space and some finite number of symmetries, and you can make an infinite trip by starting with that point, applying these symmetries. So you have a point, you apply a symmetry, go somewhere else, apply a symmetry, go somewhere else, and you can make an infinite trip that stays within omega and never comes back to where you start, to any point you've already visited. If you can do this kind of infinite trip, then there's a semi-paradoxical subset. And we saw that in the rotation case where we had a little point x and we rotate by alpha, by alpha, by alpha, by alpha. There are finite subsets that just contain one rotation alpha. So semi-paradoxical sets mean that you can travel around with our space with these symmetries, which is not a hard condition to satisfy, and travel around in an infinite way. I'll skip this, I think, and I'll move to my little philosophical musings at the end. I made a little table of a lot of cases either that interested me or that came up in the literature, and checked whether you can get invariant non-classical probabilities of the three types: conditional, regular, hyperreal, and regular qualitative. Of the interesting cases, I found only two where all three probabilities can be defined in an invariant way. The first is finite space. That's really easy. You just, for the conditional and hyperreal case, you just count up and assign equal probability to each point in the space. That's easy. The other one where it's non-trivial that you can get all three is where you have an arbitrary infinite sequence of coin flips, and the only symmetries you require are reversing a subset of the results. So flipping over a specified set of coins. If that's the only symmetries you want to respect, you can get symmetries in all the three kinds of probabilities. None of the other cases that I've thought about that seem to get discussed in the literature. I mean, there may be I may be missing some things. I didn't do a thorough survey. It was more like me sitting and thinking, what's an interesting case that I remember seeing? In all of the others, you don't have hyperreal or qualitative probabilities that are regular. Those are really hard to get. And they're strictly harder to get than the conditional ones. Because if you've got, let's see, for the hyperreal ones, what you need to do is not have a semi-paradoxical set. For the conditional ones, you need to not have a paradoxical set, which is a lot easier. And then we can sort of look through these and see what we've got. One lesson from the table is that if you want to have symmetry, conditional probabilities are more promising than hyperreal probabilities or qualitative probabilities, but not entirely promising. So here's the question that I asked myself for this philosophical question. I think about all these cases, And let's skip the finite one because that one kind of stands off on its own. But all the other cases I think about and I think, yeah, these should be symmetric under these symmetries. I have the same intuition about each of them, and I don't see any, and I don't feel any intuitive difference between any of these cases. I mean, I can see in some of them why it is that there are no answers in some of the lines in the table. But they don't, that doesn't affect my intuitions. So like in the circle and spinner case, that's the one that's the simplest one. I've thought about it a lot. That's set of rotations by an irrational angle. It's really obvious to me now that you don't have hyperreal and qualitative probabilities, but I still have the intuition that you should. That it shouldn't matter if you just add an extra rotation. You have got some game on the spinner, and you win if the spinner lands in some set, or you get some other payoff if it lands in a different set. It would be really weird to say, before learning of the result, hey, could you give it a rotation of another 97 degrees? I really want you to. In fact, I'll pay you a little bit, or maybe I'll pay you an infinitesimal amount for it. Just seems really weird. Why? I mean, it's a uniform. It shouldn't matter. And yet, we can't define hyperreal or qualitative probabilities that are invariant. And I don't feel any intuitive differences between the cases where we can and cannot. So the infinite lottery cases, if we restrict our symmetries to simpler ones like translations or reflections, we can get symmetrical conditional probabilities, but not if we allow all permutations. But it seems like an infinite lottery, you should be able to do arbitrary relabeling. In coin flip cases, we have this weird thing that, just actually noticed this today, that if you have, you can have translations and conditional probabilities that are invariant under them. You can have a reversal of a subset of results and conditional probabilities that are invariant under them. But if you combine the two, even if you just want reversals of a finite subset, you cannot have conditional probabilities that are invariant. And yet, intuitively, I want this, and I want this, and I want both of them at the same time. But what I get instead is like one conditional probability that's invariant under translations of the coins, another one that's invariant under reversing a specified subset, but not under translations. This doesn't make me happy. Well, I guess it makes me happy in this sort of perverse sense. Can't be done. So yeah, so I don't feel much in the way of intuitive differences. Here's another one that's kind of interesting. If you have a subset of the Euclidean space containing a cube in dimensions 2 or more, okay, what's a cube in dimension 2? It's a square. You cannot get any of the three things. So if you like uniformly choose a point in a square or a cube or a hypercube or something like that, you cannot get any of these three. On the other hand, if all you want is translations, you can. So if you have rigid motions, which means translations and rotations, you can't. If you have translations, you can. And you can have translation reflection of coordinates, which means you reflect just in one, with respect, you just reflect one coordinate. That's okay for conditional probabilities, but not for hyperreal and qualitative. So I don't find, so this is sort of a quite philosophical maybe question. Is there a compelling intuitive explanation of what's going on? Some kind of intuitive reason why we shouldn't have invariant probability, regular probabilities in some of these cases, but in others. My feeling is there isn't. I don't have one, and this makes me suspicious of the conditional, hyperreal, and qualitative research programs as ways of saving regularity. It seems to me that we want not just regularity, but regularity and symmetry. And the cases where we can have symmetry and the cases where we can't don't seem to cut along any intuitive lines. So to me, this is some evidence, not very strong, but some evidence for a classical approach where we just give up on regularity. Another sort of question that is philosophical question here is like, do one's intuitions differ depending on whether one's dealing with chances or epistemic probabilities? Mine do. I'm more inclined to think we should have symmetries for chances than for epistemic probabilities. Epistemic probabilities, I have a hard time actually thinking of cases where we've got like fully symmetric epistemic probabilities, like even for things like rotations. I think to myself, yeah, but if I've specified my spinner, there's going to be always some axis that is in some way epistemically privileged, only because I have to be able to describe the points differently. And when it's different, maybe, yeah, maybe the point on that axis will have a different probability from a point on a different axis. So I feel less pulled to thinking the symmetry should apply in the epistemic case. Okay, that's all I have to say.
Okay, great. Questions, and let me see.
Or answers, maybe.